All right, everyone, we are back and we are for our last problem. Here we go. Um, let's go ahead and actually let's go ahead and look at. One second here. I'm just trying to make sure that we got. Excellent. We got a little bit of a typo here. So let's go ahead and ignore this. This is just a leftover. And we'll go ahead and let's actually delete that right now. There we go. All right. So which material or which curve is the toughest? Well, largest area into the curve. I would say. I would actually definitely say anything. Probably again, red or blue would be a good choice. Red or blue. But for stiffest, I would definitely say blue looks to be a little bit stiffer, but red could be okay. Most compliant must be green. Most brittle must be blue. Most ductile must be green. Strongest, again, depends. Yield strength, I would say blue. Ultimate tensile strength must be blue. Failure stress, I would actually say red in terms of stress at failure. For the blue curve, indicate the three regimes. So I would say that we stop being linear probably around right here. Regime 1, regime 2, and regime 3 fracture right here. Write the quantitative value for the stress at failure. That would be about, I'd say, 135 megapascals. Fantastic. In the image below, so we have, whoops. Whoa. So we have, not stress, but force. So let's go ahead and there. Let's go ahead. Force supplied. Force supplied in the length of the three direction, and the length of the three direction decrease from this to this. Determine the force, stress, and the final length in the 1 and 2 directions. Material is a polymer, so my Young's modulus is equal to 1 times 10 to the 9 pascals, a gigapascal. We're told that in this 3 direction, we go, our strain in the 3 is, the final is 0.025 minus 0.03 over our initial length of 0.03. We also know that we have stress in the 3 direction is going to be equal to my strain, or my Young's modulus, and then this strain 3. And we also know that our Poisson ratio, which is for polymer, must be equal to 0.4. That's going to be equal to minus our lateral contraction, so in the 1 or in the 2 direction, over our strain in the 3 direction. So we can leverage and use all these equations. So I'm going to say E3 naught is going to be equal to 0.03. L3 naught equals 0.03. L3F equals 0.025. L2 naught equals 0.08. L1 naught equals 0.1. Young's modulus equals 1 times 10 to the 9. Nu is equal to 0.4. Let's see. And then let's go ahead and let's start to solve. So I'm actually going to say E3 is equal to L3F minus L3 naught divided by L3 naught. L3 naught divided by L3 naught. So let's go ahead and let's solve. Actually, we'll wait till this. Let's wait till it wakes up. Sig 3 equals y times E3. So we can solve for that. Good. So we have our stress. Our stress is negative, which makes sense. So let's define that. So sig 3 is equal to this. Also solve that sig 3 equals F divided by A naught. And our area is going to be L1 naught times L2 naught. So that'll be our force. Excellent. And then finally, we can go ahead and solve that for when we need our final lengths. And actually, let's go ahead and write out an expression that E2 equals L2F minus L2 naught, minus L2 naught divided by L2 naught. And the same thing with E1 equals L1F minus L1 naught divided by L1 naught. And so now we can go ahead and solve that nu equals minus E1 divided by E3. We can solve for that final length, and we see it increases, which makes sense because we're compressing, so it should expand in the other dimensions. And for the 2 direction as well. And that's it. Be prepared just in case you get a problem with calculating the stress of the beam. But other than that, we'll see you in the next video. Thanks. Bye.